So last time we started looking at the wave theory of light, and one of the things we looked at was Huygens principle, which is kind of a hard thing sometimes to visualize and stuff like that, but it's kind of an interesting way to look at how light moves from one place to another. Remember these diagrams from last time explains a couple things. So last time we had looked at it's often called Huygens principle, actually, about how light moves from one place to another. So basically, light or waves can actually recreate themselves and appear to move. Okay, so waves actually continually recreate themselves all the times, and this explains a couple things. So first of all, we looked at how this actually explains the whole d lambda relationship for diffraction, where you want the opening to be about the same size as the wavelength, so you don't have a whole bunch of point sources. You have more like one point source, or like in the right hand picture, which gives the best diffraction. So it helps to explain that, but also explains a few other things that you guys have taken. And we're going to go back to the car thing they were talking about last time. I'm going to bring back the car. So suppose you have a car right there and it's driving along, and let's get some, here we go, we're going to have some mud. Okay, there's some mud. All right, so the car's going to drive into the mud. So the car drives into the mud. Now, obviously, when the car drives into the mud, it's going to get all muddy. So I'm actually going to mud up my car a little bit. So here, I'm going to make put some mud on the tires and the bottom. It's going to get muddy. Okay, so when the car's inside of here, it is obviously going to get muddy. Okay, so initially, the car was out here and the car was perfectly clean. It goes into the mud and then it will come out of the mud. Now, if it, in reality, you guys, I mean, no big surprise, if you take this car and when it comes out of the mud, obviously the car is going to be muddy. But if the car actually travels like a wave does, when it actually comes out the other side, it would actually be clean. It would only actually be muddy while it's actually in the mud. Now, this may seem really stupid, but this is exactly what light does when it travels through materials. Okay, so before it was clean because it's on the clean road. In the mud, it's muddy because it's in the mud. On the other side, it's clean because it's on clean road again. And again, it may seem really, really stupid, but this is exactly what light does when it goes through material. So let's go back to what you guys have done previously. Okay, suppose we're taking like some of that. Actually, we'll make it a bluish color. And then, actually, let's change it. That's more like purplish. Whoops. Let's change it to, there we go. And we'll do that. Okay, so when you guys took light way back when, a couple videos ago, and we talked about light coming in, and suppose we got some light coming in right here. It then goes into glass. We'll say this is glass, and obviously when it goes into the glass, it's going to slow down, right? And then it goes into the air and speeds up again, so something like this, all right? So when you guys did light, and let's say this is air, so here it'd be going around 3 times 10 to the 8 meters per second. Here it's going 3 times 10 to the 8 meters per second. Inside the glass, it is going around, well, it's going to change a little bit, but give or take a little bit, it's going around 2 times 10 to the 8 meters per second. Well, there's no difference between this and the car type thing. When it was in the air, it traveled at the speed that it does in air. When it goes into the glass, it has the speed that it has in glass. And then when it goes back into the air again, it magically just goes back up to 3 to the 8? Well, no. It takes on the speed it's supposed to have in the air, the glass, or the air, depending on where it is, right? So the same way that the car would be totally clean, only be muddy in the mud, and then be clean again, same thing for the light. In air, it has the speed of light in air. In glass, it has the speed of light in glass. Over here, it's back up to the speed of light in air again. It only has the speed of light in glass when it's actually in the glass. The same way the car is only muddy when it's actually in the mud. So it sounds kind of weird and strange, but this is what you guys were working on a while ago. Okay, now this also helps to explain something else that you guys did when you guys did your refraction and your Snell's law and all that kind of stuff as well. Even if you just go to this part right here, oops, wrong tool, this part right here, just on this side, it's got 3 times 10 to the 8. On this side, it's got 2 times 10 to the 8. The speed changed. Same thing here. Between here and here, the speed changed. Well, if the speed changed, shouldn't you have an acceleration? And if you have an acceleration, shouldn't there be a force equals to ma, blah, 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 that type of stuff? Well, no, there isn't, because light doesn't accelerate, because the light on this side and the light in this side, they're not the same light. It's been recreated in the glass. Since it was recreated in the glass, it takes on properties of being in glass, which is the 2 times 10 to the 8. Same thing on this part. It didn't slow down. The light that's on this side in the glass and the light that's on this side in the air is not the same light. It's been recreated in the air, therefore takes on properties of being created in the air. So again, it's kind of a weird idea. It's really, really strange, but actually explains a few different things. There's actually a lot more things it explains as well. But that's one of the other things, the biggest things you guys have worked on is light changing speeds when it goes from one material to another material. But you have a change in speed, but there's no acceleration, there's no force. Well, that's because it's not the same wave. It's been recreated in that material and therefore takes on properties of the material. The same way the car that was clean was not the same car that was in the mud. It was recreated in the mud, therefore takes on properties of being in mud. And then when it got out of it on the right-hand side, car that was in the mud and the car that was outside the mud, not the same car. It was recreated past the mud and therefore took on properties being past the mud, which just means it was still clean again. Okay, so again, it's a kind of it's pretty abstract, it's pretty weird, and the more stuff that you take about light, the more abstract and weirder it really gets, and it can get really, really strange. But it really helps to explain some things like the whole d lambda thing, that type of thing. It also, like we're just talking about, explains light changing speeds in materials. Okay, and I'm going to put changes in quotation marks because it doesn't really change. So it explains light changing speeds in materials with no acceleration or force or any of that type of stuff. So it's all about recreating, which is actually a really, really important idea that comes up later on in a year or 2 or 3 or 4 years, depending on how much light and physics you actually do. Okay, so again, it's kind of neat. All right. So this helped to explain the whole d lambda type thing, and it worked out pretty cool when they actually started applying this like in the 1800s and that type of stuff to the light theory that was actually going on. And once they had this, there pretty much wasn't anything else that light theory in terms of waves couldn't explain. There's still one thing that we'll get to a little bit later on, but this really helped explain the lack of diffraction for openings and stuff like that. And once they started making the openings a lot smaller, like in this picture, then they could actually see the light diffracting really, really well. So with this idea applied to light and how light can travel like a wave and recreate itself and that kind of stuff, they say, you know what other type of wavy things could light do? So is there an actual, is there some kind of other test for light as a wave? Is there something else that light could be tested for to see if it truly is like wave? Well, what other wavy things do waves do that we could try with light? And there is absolutely. And one of the biggest things that you guys have done that all types of waves do is they can cause interference with each other. Waves can build on each other and waves can cancel each other out. And you guys have done a bunch of different stuff like this, where waves are coming together and make bigger waves, smaller waves, that type of stuff. Now, one of the biggest things that you guys did with this, let's see if it looks familiar, is something like this, or more specifically like this, where you guys had the two-source interference pattern, where you have two sources of water, and you have the water waves going, and the water waves will actually create an interference pattern. Remember, we had the maximums in the middle, and then we have minimums here where the waves canceled out. Same thing here, maximums. We did the S1 minus S2 over lambda equals, integer plus a half, or in between type stuff. Water waves do this all the time. You can actually see it no problem. Well, sound waves can do the same type of thing. You can do the exact same type of thing with sound waves. In fact, if we were in my lab, I could show this to you, where you can actually go to places and hear the sound to be loud. There, the sound would be quieter, louder sound, quieter sound, louder sound, and you can actually do this thing with sound. People who do things like acoustics in concert halls and home theaters will actually look at this type of information to figure out for better speaker placement and stuff like that. So they thought, this works with sound, this works with water, both types of waves. You should be able to do the exact same thing with light. So that was a big question that they had. Can you actually create an interference pattern with light? Now that may seem kind of strange, because if this is true, we'll pause this for a second here. Suppose these are light waves. Well, if these are light waves, it's not about like ripples or how loud stuff is, it's about brightness. So if this would be true for light, if this actually were light, well, right in the middle here, it wouldn't be loud or wavy, it'd be bright. Here would be really, really bright. Maximums get bright, but at a place like this and a place like this where there's flat waves, in terms of light, it would be dark, which doesn't seem to make any sense. How can you put two light sources on the same location and get black? That doesn't make any sense. So this is what they wanted to actually test for. Now, of course, one of the tricks or the hard parts to actually do this is, in order to do this, you need two light sources. And to do it properly, they must be identical. They must be identical to each other and synchronized in everything. Now, how do you get two light sources to be perfectly identical, especially this like 200 years ago? How would you possibly do this? Well, they thought about it and they sort of figured out, well, you could actually do this if Huygens' principle was actually right. So to do this, you could actually use Huygens' principle. Because if light recreates itself, instead of taking a diagram like this, you have a big wide opening, if you shrink it down like this guy, you get a point source. Well, what if instead you put a barrier in here, something like this? Instead of using one hole, use two holes. Well, then you could create two guys like this, close to each other, and create two wave sources that would be perfectly matched, perfectly synchronized, and perfectly identical because they actually came from the original source. So basically, take this idea and put it there and there by using one hole instead of two holes. Okay, so let's go back to a little simulation. So here we have a wave generator back here. So there's the waves coming in. And we have a little opening here. And of course, when they go through the opening, they will diffract. And you can see, there you go. Okay, we got some round waves. Now, of course, flat waves are turning into round waves. No, remember, they don't turn into round waves. Flat waves don't turn into round waves. They're not the same wave. So right here, we've got a little point source being created, which allows for those nice round waves. So the idea was, instead of using one opening, use two openings, and then they'd be perfectly identical, and then they can actually create a interference pattern. Okay, so that would look something like this. So we still have the source there comes in, and then if we go through something like this, we still get an interference pattern with the water waves. So it doesn't make any difference if you use two sources or use one source and turn it into two sources using Huygens' principle, which really showed the Huygens' principle actually had some basis to it. So the idea is, take one light source, put it through here, make two identical light sources out of it, and get the interference pattern, something like that, and see if you could analyze it. So again, you can do this with water. They did this with sound. It works. But of course, the big question is, will this type of thing work with light? And it sort of puts a few things together. It sort of shows, is Huygens' principle right? Does it actually have more foundation? Do waves recreate themselves? Does light travel as a wave? There's all these things sort of have to all fall into place at the same time and all work properly to actually make this work. And of course, the biggest question is, how is it possible to have two light sources? And, light getting brighter makes sense, But light hitting light and getting black, that didn't make sense. But that's what we will look at next, is the actual experiment and what actually happened.